Astronomers have discovered the biggest and most distant black hole collision ever observed. The massive event was one of 4 new black hole mergers detected as scientists sifted through the huge archival data streams generated by the first 2 observing runs of the LIGO Gravitational Wave Observatory. The findings, reported in the journal PRX, indicate the event, catalogued as GW170729, occurred during LIGO's second observing run on the 29th of July 2017. It was the most massive and distant gravitational wave source ever observed. The merger, some 5 billion light-years away, involved the collision or coalescence of 2 stellar mass black holes, one about 50.6 times the mass of the Sun and the other around 34.3 solar masses. They merged to form a black hole of some 80.3 solar masses, in the process releasing around 5 times the mass of our Sun in pure gravitational energy. Scientists also found the event involved black holes spinning faster than any other merger so far. The other 3 newly detected black hole mergers ranged from 2.5 to 3.9 billion light-years in distance, resulting in the formation of new merged black holes between 56.4 and 65.6 solar masses. The 4 new discoveries mean that in just 13 months of gravitational wave observations, no less than 10 stellar mass black hole binary mergers and 1 binary neutron star merger have now been detected. That's almost 1 a month, and we're only just starting. The neutron star merger was especially exciting as it was observable not just using gravitational wave observations, but also conventional optical, radio, infrared, X-ray, gamma-ray, and ultraviolet telescopes. And it may have resulted in the birth of a new black hole. LIGO, the Laser Interferometer Gravitational Wave Observatory, comprises 2 identical facilities located in Livingston, Louisiana and Hanford, Washington State. Each LIGO observatory fires lasers into a beam splitter, which then shoots the beams along 2 perpendicular 4-kilometre-long tunnels equipped with mirrors at the far ends. The reflected laser light is then sent back to a detector, where eventually the 2 beams should theoretically recombine, provide some sort of interference pattern. As a gravitational wave, generated by a moving mass, say merging black holes, passes through the cosmos, it causes the very fabric of space-time itself to stretch and compress ever so slightly, by just a fraction of the diameter of a proton. When a gravitational wave passes through the LIGO detector, local space-time, including the 2 beamlines, reflected lasers, are each alternatively stretched and compressed ever so slightly, leaving them out of phase, the telltale signature of a gravitational wave event. Using multiple gravitational wave detectors allows scientists to determine the direction of the wave source. And the addition of a 3rd detector called Virgo, located near Pisa in northern Italy, has further improved gravitational wave detections. And a 4th gravitational wave detector, originally offered to Australia but rejected by the then Gillard Labor government, is now being built in India. From September the 12th, 2015, through to January the 19th, 2016, during the first LIGO observing run since undergoing upgrades in the program called Advanced LIGO, gravitational waves from 3 binary black hole mergers were detected. The second observing run, which lasted from November the 30th, 2016 through to August the 25th, 2017, yielded a binary neutron star merger and 7 additional binary black hole mergers, including the 4 new gravitational wave events. It took science a century to confirm Albert Einstein's prediction for the existence of gravitational waves. And now, in less than 3 years, gravitational wave detections have provided direct evidence for the existence of black holes, another prediction of Einstein, as well as binary black hole and neutron star collisions. The LIGO detectors are now undergoing another upgrade to further improve their performance. One of those working on the project and one of the authors of this study, Professor Susan Scott from the Australian National University, says the new window on the universe being offered by gravitational wave observations has revealed just how frequent these mergers are. Scott says these detections of black hole collisions greatly improve science's understanding of how many black hole binary systems there are in the universe, as well as the range of their masses and how fast black holes spin during a merger.
What we've done is, after the finish of the 2 observing runs of LIGO and Virgo, 01 and 02, we've re-cleaned the data and we've recalibrated it very carefully. And in addition, we've refined our searches. For instance, enlarging the parameter space over which we search. And with that combination of things, it became a good thing to do to actually go back and analyse all the data from the two observing runs. And with the increased sensitivity, we managed to uncover 4 amazing new binary black hole inspirals and mergers. So we were extremely excited about that. We had 5 announced previously, and that was the other good thing about going back and reanalyzing the data. We were able to further refine the significance of our earlier detections and announcements and better estimate their parameters. And in so doing, this October event in 2015, on the 12th of October, was elevated to a gravitational wave detection. So the 5 became 6, and then we've added 4 more.